change dramatically. So in few slides you will see how big it's going to be the change that we are going to face. New architectures, new software will come in place, and the things that we need to be prepared about that thing. And it's not just one guy or one woman dealing with this kind of duties, so it's supposed to be a community effort, and we will need a lot of collaboration in this area. So that's why this is a nice space to share this kind of knowledge. So here you have logos. Probably it's the only logos that you're going to see, and the only advertise that you are going to see on the complete run of the conference. If you look at the program, all the talks are very, very technical, so no commercial stuff. It's expected for these days. So let me start with new architectures. So the new trends seems to point into bigger systems. So more cores per socket, more sockets per node. To the point that, well, if you look at here, Intel Skylake, which is going to be available sometime next year, 28 cores per socket and up to 8 sockets per node. This means 200 something cores per node. Okay, gigaflops per node. Probably several of you, if you have an NDAR design with Intel or ARM or IBM, you may know all these numbers, but this is an open session, so I can provide this kind of numbers, okay? Same thing for Intel Knights Landing, 72 cores up to 288 threads. So number of sockets per node is 1, 3 teraflops in one small box. So we are looking to a really high performance in a small system, and when you lose this system, well, you lose a lot of performance, right? So the investment for several companies in predicting hardware errors are really high, and at this time, many of them can be predicted, and you can trigger something in the batch queuing system, to do something, like training the node, migrating jobs, and whatever. So we are going to discuss about all these technologies as well. So in addition to that, it's not only having this massive number of CPUs in just one box, the instruction sets have been improved quite a lot. So if we move back to the ages of Intel Westmark, where we had just 4 flops per cycle, Sandy Bridge moved to the double, and we have seen a lot of improvement. Then Haswell, which is what we have now in the market, is 16 floats per cycle, but we have seen that not all the codes are capable to maximize the utilization of AVX instructions, the vectorial supportability. And we are going to Skylake, which is going to improve the number of resistors for AVX up to 32. In theory, so it's 32 times the gigaflops that you have there multiplied by the number of cores that you have there. So it's a huge performance improvement in pretty much no time. Okay. So this will change the way we understand at this stage the HPC resources that we are dealing with, and it may require to change some lines of code, to maximize the performance of the code that can run on these architectures. So this is an overview for for Skylake. So if you have 2 sockets factor, you have 2 links, UPI, ultra-path interconnect, connecting them. If you have 4 sockets, you could choose 3 that kind of sockets that have 3 UPIs, so 3 links, and then you can develop something like this. Okay, so in this situation and in this situation, the access 2 other CPUs, it's completely symmetrical, okay? But if you choose 8 sockets, you only have 3 links. So if you want to communicate this CPU here with this other here, you need to go this way or this way. This is the easiest path, right? So that the most performant, so that in order to get the maximum performance is to communicate with the neighbors. So it's, in this case, the number 1 will be able to communicate with the 4, 2, and 5. Okay, if you want to communicate with the number 7, can you see the path? So it's going to drop the performance dramatically. So that's why C groups in this space will be really, really important. And it's not just a matter of allocating CPUs in a node. So the batch queue system should be able to take into account this information. New methodology, it's going to be important in the near future. And at the same time, for MPI jobs, distributed memory, so we need to, since you have several hundreds of cores in the same place, you want to reduce job scattering. You don't want to have one core using one core working in this CPU, another one here, and then another one similar kind of allocation in another node. So if you can move all the stuff in the same place or using less nodes, it's going to be much better in terms of performance. Less latency overhead, more bandwidth because you're working in the same node. So this is something that needs to be developed. It's not yet developed. So a mechanism that could reduce the job scattering. So we do have this mechanism, but there's room for improvement. So the other thing is that in order to enable vectorization and in order to take advantage of parallel, so in order to take advantage of vectorization, you need to do some changes in the code, right? So this is the simplest thing I found, okay? So if you are in computer science, if you're a computational scientist, you may know what it means. So this is the simplest way. So in order to enable that thing, just changing the wording here and the way you read and write the variables is going to be key for this. So take into account that if your code is not able to take advantage of vectorization, you are losing 32 times the performance. Okay, so there's an overhead copying data into the registers, but then after that, if you need to operate quite a lot, it's 52 times. So it's keep in mind that thing as well. So new fabric technologies. This is another key component in terms of hardware that's going to be available in near future. So OmniPath is probably the most well-known at this time. It's the new future technology that's going to be available quite soon. So the fabric is going to be inside the chip. So there's no longer requirement to go to the PCI bus in order to communicate with other kind of nodes. So that's why the latency has dropped quite significantly. Bandwidth is quite good, so it's 100 gigabytes per second, and then the number of cores per switch, which is quite new, this thing. So usually what we have been dealing with these days, it's 36 with Mellanox. Nowadays we're going to have 48. So this means bigger switches, less complexity in terms of topology in the low latency network. And in the next generation of OmniPath 2 will adapt the technology that Intel bought from Cray, it's Aries technology, with this adaptive routing. So this is going to be available on a regular market as well. So for Mellanox, they have invested a lot of time and R&D, and they have improved the bandwidth quite a lot. The latency is not yet public available. The switches seems to be on 36. Maybe in the future it's going to change. But the key component on the new technology that they are offering now, it's a way to deal with the collectives inside the switch. So the CPU no longer needs to deal with it. So the collectives can be offloaded into the switch, and the switch will take care of that thing. I have an early access to this technology, but sooner or later we will have access through regular market or through early access. So we're talking about several hundreds of cores per node, bigger switches. Okay. Maybe if your code is not able to scale up to several thousands of cores, there's no real need for non-blocking configuration. So this opens a new possibility to cheaper topology, low latency topology, and this is a proposal. So three ring topology based on just three switches will be able to provide a huge power, computational power. So using fat nodes like 4 sockets or 8 sockets per node, taking into account this new topology, and then minimizing the cost overhead on low latency, we'll be able to allocate the jobs quite easily. And then if you are using a Blasco system that is able to deal with topology awareness, scheduling, like a Slurm or many others, you can define like 2 layers and avoid in this way to inject a lot of scattering in the system. So to reduce the scattering, we'll be able to provide better performance as well. So this is an example. So 3 switches, 32 ports is going to be for the regular compute, and 2 links per switch. So this is a topology with an 8-to-1 blocking. So in this case, for example, a Slurm could say, well, wait for 30 minutes, and if I don't have allocation for my MPI job, then use whatever you have here, okay? But in each box, you will have 5,000 cores, maybe. So it's really hard to find this situation if your jobs, if your codes are not able to scale up to more than 5,000 cores, something like this, okay? If we are looking at Omnipath, we're talking about 44 ports, similar kind of stuff. The blocking, it's element 1. How much time I have? Yeah. So if you go further, you could even set up something like this. So 4 switches, and then so you will have here around around 122 ports available for switches, for nodes, and so it's going to provide a lot of compute capacity. To the point that with these technologies that we are going to have in 1 year, so this is the top 500, the current top 500. So at the bottom, at the top 500 position, we have the QSpace 2, and at the top 1, Tianhe, the second release of Tianhe. So 16,000 cores, 206 teraflops. This is Limpak, okay? And the top, so 3 million cores, it's massive. 34 petaflops. Okay, if I develop something like this, based on Omnipath interconnect, which means something like this, 44 cores, only 3 switches, and 4 sockets per node, and here, currently here. And this is going to happen next year. Okay, I don't need too much stuff to be in this business. And if your code is, again, not able to scale up to that limit, that's perfect. Limpak can support that thing and will generate this. So the calculation is pretty simple. I'm assuming, this is a simulation, this is not the real data, okay? So it's just a guess. But guessing that I have 112 cores per node, 2 to 6 gigahertz per core, I will get this is R peak, and assuming a 60% of efficiency, which is terrible, okay, it's really, really bad efficiency, I'm getting here. Sorry. So well, if you need if your code is able to scale up to that limit, then as always, Dragonfly, battery, Omnipath, interconnect, it's going to be your friend. Okay. 4 parts. For temporary loop, you have several technologies there. So the key thing is to be able to avoid to share this common area. So that's why BGFS on the one it's really good at this stuff, because you will have a dedicated metadata and storage servers for that. Similar stuff for create data wrap and SCI SEO copy. In terms of code portability, Linux containers will play a key role here. But Linux containers will be able to provide a new infrastructure or framework in HPC workloads without impacting the performance. But this is a typical slide that probably you have already seen, so there is no overhead based because of the virtualization. Okay, so for the system it's just a process, so no overhead here. So Docker is probably one of the most popular frameworks to do application packaging. But one of the key features of Docker, for example, is not going to be suitable for HPC, because in HPC what we want is to build applications on the hardware that we are going to run in order to get all the instruction sets that are available in the cluster. If I compile the code in a Westner, I definitely can run that thing in a Skylake, but not the other way around. Okay, and at the same time, I will lose a lot of performance. How much performance? 52 times at least. Okay, so that's why it's really important to take that thing in mind, to keep that thing in mind, and avoid to use Docker Hub, for example, which is one of the key elements in Docker popularity, and use your own facility to generate these images and pull the images from there. In order to minimize the overhead of building applications, there EasyBuild is going to be a key component on many places here. In this room, there are a lot of contributors on this community-based project, and Alan somewhere here is going to introduce this nice project here. I'm not going to spend too much time here, but it's going to be your friend, definitely. So the rooms for improvement, MPI and Docker, well, Linux containers in general, is not working nicely at this time. So if you have played around with Docker Shifter, which is the Cray version of Linux container, it doesn't allow more than one MPI job in a node. And because we have hundreds of cores there, it's the probability to have to deal with that thing, it's quite high. So something needs to be done here. Okay. At the same time, hypervisor technologies for Linux containers are going to be really, really key. And LexD, it's one of the key, or it's what is generating a lot of expectation in HPC world. Lucky us, we have Stefan Graber coming from United States. It's going to talk about that thing sometime today. And it's the main developer of LexD. And this will open new ways to deal with the Linux containers, and new ways that are really, really key for HPC. It's not just a matter of security by design, which is what is the main concern for several of us. Okay. Nowadays, if you want to run a Linux container, the only way to run that thing in a cloud is using this Linux container in a VM, and then you are losing a lot of performance for that thing. Okay. With LexD, you reduce this overhead because you are using clearly this approach. So it's scalable, it's intuitive. Important thing is that it's hardware agnostic. It's not only Intel based, so it runs on ARM and Power and whatever you can imagine. And for me, this is personal opinion, live migration, this is really, really good. If you have been dealing, or the people that knows me, have how much I invest in checkpointing and restart. And if you have been dealing with a VLCR, the NTCP, native checkpointing, well, this is huge. This is a lot of overhead. It's by far really, really complicated. Dumping a lot of memory into the share file system to be able to migrate the job to a different place. It's going to be really, really challenging when your job is really, really big and demanding in terms of memory. So that's why, if you, Stefan, if you want to make all these people really, really happy, live migration with MPI support, it's really, really thing to look at. And yeah, same thing. LexD is working for that thing. OpenStack is the natural evolution for that thing. People, companies like Craig are looking at this technology, this software package for deploying images in the system. And there's no surprise here. LexD is developed by Ubuntu. Same thing for Stack, OpenStack. More things. No more things. So I think that this is the last slide. Federated Sloan cluster support. This is going to be really, really key for open new ways to collaborate between HPC facilities, and it will reduce significantly the complexity of cloud bursting. So this is another technology that we should look at. In fact, this could be a really good mechanism to reduce the job scattering, MPI job scattering, because you can move stuff around and allocate the resources as you need. Okay, so that's all from my part. And again, to get ready for all these challenges, we need to collaborate, and this is the place to be. This is the place to start these collaborations, and I hope you will enjoy these 2 days. Thank you.
Thank you, Jordi.